So when you're doing these, just to point us in the right direction, when we're looking at double bonds, who can do double bonds? Carbon, nitrogen, oxygen, sulfur, and for our purposes that's good enough for right now. But what about this? Triple bonds. Carbon and nitrogen, only ones that can do triple bonds. Alright, so keeping that in mind as we proceed forward then, okay, when we look at H3PO4, it will just come with practice on what element goes in the middle. So if this is our compound, H3PO4, you're always going to put carbon in the middle. If carbon's not there, nitrogen would go in the middle. But in this case, we would put phosphorus in the middle. So we're going to start with phosphorus. Okay? And phosphorus is in what column? Okay? So again, you can put unshared pair of electrons together, but maybe follow the bus seat rule by going in this fashion. And then here's an unshared pair of electrons up there. Okay, so now we would branch to the outside, and it's the hydrogen ions that get stripped off of there, so they go on the very outside. So we would not want to put those those hydrogen atoms here. So with that, if we put an oxygen here, what column is that? Then you do the same, not phosphorus again. Do the same thing down here. And when you're putting them dots and X's next to one another, you're creating a bond. So you would work your way all the way around with those oxygens, but you have 4 of them. So what we can do is create a coordinate covalent bond and do one of these. Okay? So you'll notice that how many electrons short is that oxygen? Okay, where do you suppose it gets it from? So you'd put a hydrogen ion there, and I put too many down here. Oops. Then you do the same thing down here, and then of course you rotate yourself around, put another oxygen on there. Then you'd have your H3PO4. And SO4 with a negative charge is very similar to that. You'd put sulfur in the middle. And one thing I may possibly say is, oh, how soon we forget. We probably did these in physical science 2 years ago. But that was 2 years ago. I get that. So with that, we talk about ozone, which is O3. That means it's got a resonance structure. It means multiple bonds can rotate around each other. So ozone is this. So what would possibly happen is you may try doing something like this and trying to get them electrons to balance around and say, well, here's 6. Then you're going to try to put an oxygen here, 1, 2, 3, 4, 5, 6, and then another oxygen over here. What's the problem that we have right now? Okay, this oxygen's got 8, but these 2 are both 1 short. So when a single bond doesn't work, what does that tell you you need to do? Try a double bond once, okay? So, and if something doesn't look right to begin with, then just erase the whole thing and start over. That's the best thing that you can do. So what that means is if we create a double bond, there's 1 oxygen, we'll put another one here, And E's, slashes, dots, whichever, I would advise that don't use X's for all of them. Otherwise, it's very difficult to see which electrons are coming from which atom. Now, when you look at this, we are short one oxygen, but where could that possibly bond to? Either got to be one of these two, but just like that H3PO4, on that top of that phosphorus, we said we would create what on top of there? A coordinate covalent bond. Okay? So with that same type of knowledge, we could put an oxygen over here. Okay? And then upon doing so, go ahead and put that oxygen on the right. Oh, I did that wrong. That's not what I wanted to do. Darn it. Okay, so this is still double bonded. That's right. This is what I meant to do. Okay, is create two double bonds. Oh, that's not right either, because that one's going to have 10. I had the right idea, I just put it on the wrong spot. That's what I meant to do. We're doing the same thing, but it needs to go down here because what happens is that multiple bond can rotate from one side or another, and that's evident on the back page. So if the double bond is not on the left side, where could it be then? On the right side. So what that would mean then is it would look like this. And then how would you finish that? You put another oxygen here and do what? Would you put any electrons in here? No. They all 2, 4, and then 6. And that would be a resonance structure because either the double bond is on the left or the double bond is on the right. And no, it's just in the structure there's ozone that exists where there's a double bond on the left side of the molecule. There's double bonds where it's on the right side. It's the same formula, but the structure's different. That's what a resonance structure is showing you. Okay? So with that, SO3 is another one because that can have double bonds to it as well. And if you really wanted to, I'm sure this same problem was in your textbook in the chapter showing you what resonance structures are. That's how you got it. Okay. Oh, resource. It's actually in the book. Oh, open up the book. Oh, there it is. Yeah. Okay. All right. So then there's another one on the back. What was it? C3NO or CH3NO or something like that? I can't hear both of you. Sorry. Just one of you. CH3 and H2. Yes. Okay. So then what we had said is if you're looking at that compound, what do you think you would start with in the center? Which element? Could be nitrogen, but either carbon or nitrogen. So let's go ahead and try a carbon atom. And just through trial and error, are you going to do a triple bond right away? Probably not. So let's try a single bond. In other words, 4 go around here. Okay. So let's try, now that we got our carbon out of the way, what do you think we should try next? You can do your nitrogen, and Let's try a bond here. Okay. So there's one. How many more does it have? It's got 4 more. So we could do 1, 2, 3, and then here's an unshared pair up here. So there's our 5 electrons. So, does it look like it would be fairly simple to finish from this point on? Okay, because this carbon's still missing 3, but it's got 3 hydrogens. This nitrogen is missing 2, but you still have 2 hydrogens. Okay, otherwise, if we just do this, I saw that on papers, that doesn't make much sense. Okay, I mean, you can do that as long as you maybe put another hydrogen here, but then it just looks kind of silly if you don't account for that electron. You would rather have that as a dot or a triangle or an E or any one of those. Then it's easier to see how these actually bond together then. Okay. Yes. Yep. Yeah, no, that would not work. No. So one of the, I said I was going to hand them out. I'm going to, and what I want you to do is look at this. And some of these compounds are on here twice, but that means one has to be done with a triple bond, the other one has to be done with a double bond. What I mean by that is look at the back page, and the second row down in either column has got C2NH3 and C2NH3. So one has to be done with a double bond between the carbons and the nitrogens. The other one has to be done with a triple bond. Okay. Also, C3H6O, I believe is on there. No, yeah, it is on there twice. It's on the front and it's on the back. Also, that has a single bond, a double bond and a triple bond. Okay. So a lot of this is just trial and error, satisfying the octet rule with multiple bonds. So, is there anything else on that first page that was handed out that you are maybe struggling with? Okay? One more. Like this one right here. Like that. Okay? So, what column is sulfur in? And you may be wondering, well, how would you know how to, oops, I did that wrong. How would you know how to balance these electrons around like that? Well, if you have 4 oxygens, you're going to want that around all 4 sides. Okay, that would be their first indication. So, we need to knock out an oxygen. You tell me, top, bottom, left, or right. Okay, so we can create a single bond there, it looks like. Okay, now where? I know we're one short, but we'll come back to that. Now where? Okay, we're getting the easy ones out of the way. Okay. Okay. How would we make a bond here? Well, if we did that, just for argument's sake, let's try it. How many does that sulfur have around it now? 10, yes. So a double bond doesn't work. So these two bottom X's, what does that tell you to do with them? Put them on top. Okay? What about down here then? Same thing. But then these two are one short. But what does it tell you up in your original compound that there's two extra what? Not protons, electrons. So what do you suppose we'd put here? A dot, an E, a triangle, whatever. There and there. Then you had already said you'd put another oxygen down there. That would be correct. So then, let's say you had this compound, H2SO4. Now, these electrons, they're still there, but there's another element that you're accounting for, the hydrogen. So then you would put a hydrogen there and a hydrogen over there. That's gone then. Yep. Okay. So, why don't we just give you the rest of this time to go ahead and work on these, and we will pick up with this information next week.